Foreign is expanding in 1929, revealing that we are made of chemical elements forged in the centers of stars, as discovered in 1957. The sky isn't just pretty to look at, it's a window to the insanely powerful universe we live in. There's so much going on out there that we on Earth are usually totally oblivious to what's really happening. Why are we here? Why do we have stars and galaxies? It could have been something else entirely. Even when these things eventually affect us, we tend not to pay attention until matters get too serious, and well, that might have happened again. Throughout history, Betelgeuse has been one of the brightest stars in the sky, but now it has begun vibrating violently, and something terrifying is occurring. Join us as we bring you all the details about what's going on with Betelgeuse and how it might just change our future along with its own. Betelgeuse isn't an ordinary star, it's never been. It's one of the biggest stars ever discovered, so massive that it even makes our sun look small in comparison. With a mass roughly 20 times that of our sun, Betelgeuse bears the undeniable mark of a supergiant star, and that's exactly what it is. Perception can be deceiving though. From our vantage point, Betelgeuse might appear as just another distant star, but in reality, it holds a status far more profound. Located more than 640 light-years away from Earth, this distance might seem inconsequential at first glance, but in cosmic terms, it's monumental. If we had the capability to travel at the speed of light and notion beyond our current reach, it would still take over 640 years to bridge the gap between us and Betelgeuse. Under normal circumstances, it would take over 12 million years to make the connection, which is longer than the entire course of human civilization on Earth. This puts into perspective how powerful this one star truly is, and now it's been vibrating violently. We see stars as calm objects in space, just existing regardless of their size, but this one proves that's not true. These vibrations have scientists confused, as Betelgeuse has never been still in the first place. It's always been known as a pulsating red supergiant, changing constantly. When the star expands, it looks brighter, and when it contracts, it appears dimmer in the sky than usual. These fluctuations in luminosity take place over extended periods, ranging from tens to hundreds of days. What's even more interesting is that Betelgeuse showcases a wide range of brightness, spanning from approximately 0.5 to a more intense magnitude of 0, a massive difference for stars. These shifts in brightness actually occur in recurring patterns, with the shortest cycle lasting about 185 days and the longest extending to around 23-35 days. But sometimes, these fluctuations can be more periodic and follow a more defined pattern, which can be recorded. This phenomenon is called V-band magnitude. In February 2021, it registered one of its lowest V-band magnitudes in recent times, measuring at 1.614. While still relatively bright, this marked a departure from the customary radiance associated with Betelgeuse. Betelgeuse's significance isn't solely defined by its luminosity variations. Its distinct reddish hue stems from a cooler surface temperature of around 3,500 Kelvin, notably cooler than our Sun's 5,500 Kelvin. That might sound strange because, as mentioned, the Sun is smaller than Betelgeuse but is still brighter on any given day. As it's cooler, it's going to be the polar opposite of our Sun. This cooler temperature also leads to reduced energy emission per unit of surface area, resulting in its perceived dimness despite being one of the largest stars known to us. It has mostly been a relatively stable star, even though it's a pulsating giant. So what could the recent change from calm to storm be? Well, that's where things get complicated. One of the most popular explanations is that Betelgeuse's helium shell is burning. As Betelgeuse evolves through its stellar life cycle, it gradually exhausts the hydrogen in its core through nuclear fusion, converting it into helium, expected behavior for a red supergiant. As hydrogen fusion slows in the core, the star's outer layers expand, causing it to swell in size. This phase signifies the star's transition into the red giant stage. During this stage, helium accumulates in a shell surrounding the depleted hydrogen core. The intense heat and pressure in this helium-rich shell initiate a secondary nuclear fusion process known as helium shell burning. Helium nuclei begin to fuse together, forming heavier elements like carbon and oxygen. This process releases energy, counteracting the gravitational force trying to compress the star's outer layers. However, helium shell burning isn't as stable as hydrogen fusion in the core. It can actually lead to periodic energy buildups and releases, steering the star down an unexpected path. These fluctuations in energy output result in instabilities within the star's structure. The increased energy production causes the outer layers to expand, while the subsequent energy release causes them to contract. These expanding and contracting motions manifest as pulsations, causing Betelgeuse's brightness to vary over time. The intense energy generated during helium shell burning can lead to strong stellar winds, especially in red supergiants like Betelgeuse. These winds carry away a significant amount of mass from the star's outer layers. The mass loss due to these stellar winds contributes to the redistribution of matter and energy within the star, further influencing its evolution. The outer layers pulsate outward during expansion and inward during contraction, like rhythmic breaths. This rhythmic pulsation is like the heartbeat of the star, and when observed we see it as changes in luminosity. While it's possible this is what's happening, more steps must be followed to confirm it. Astronomers use a range of techniques to unravel the mysteries of pulsating stars like Betelgeuse. Among these, photometry and spectroscopy stand out as key methods, each shedding light on a different side of things. Through photometry, astronomers monitor the star's luminosity changes over time, capturing the amount of light emitted at various intervals. As Betelgeuse pulsates, its brightness fluctuates, revealing insights into the underlying processes causing these variations. This method provides a direct link to the star's dynamic behavior, allowing astronomers to track its luminous output. Spectroscopy offers a more nuanced perspective, analyzing the star's emitted light across a spectrum of wavelengths. This technique reveals information about the star's temperature, composition, and motion. As Betelgeuse pulsates, its spectral lines shift and broaden, offering a glimpse into the physical conditions within its outer layers. These spectral changes can be studied to gain a deeper understanding of the mechanisms driving its pulsations. By combining these techniques, astronomers create a comprehensive narrative of a star's pulsation behavior. Photometry's luminosity measurements complement the insights extracted through spectroscopy, forming a synergy that deciphers the connection between the star's interior processes and observed luminosity changes, painting a more holistic picture of Betelgeuse's rhythm. To explore the inner workings, astrophysicists use computational models to simulate the star's internal dynamics and behavior. These models include a range of factors from equations governing stellar structure to nuclear reactions and fluid dynamics within the star's core. Replicating these processes virtually helps bridge the gap between theory and observation, making it easier to figure out what's really going on within the pulsating star. Deep within stars like Betelgeuse, a remarkable process known as stellar convection can occur. This mechanism transfers energy from the core to the surface, balancing internal processes and outer radiance. It involves the movement of matter within the star due to temperature differences. At the core, immense heat causes surrounding material to expand and rise. Meanwhile, cooler material from the surface sinks toward the core, creating convection currents that transport energy. This cycle of rising and sinking material forms dynamic flows, functioning like a celestial conveyor belt. The rise and fall of hot material can cause fluctuations in energy transport, leading to changes in brightness. In binary star systems, material transfer can influence the lives of the stars involved, potentially initiating pulsations. Depending on the size and distance, the gravitational interaction between two stars can lead to material transfer, significantly affecting their evolution. Even supergiant ones like this have always focused on stars being individual celestial bodies. It wasn't common to study how two stars interact with each other, let alone have actual transfers of energy between one another. But this isn't just a theory, this happens, and it's been happening throughout space for centuries. It's just the fact that now we have access to telescopes and research teams that can go in depth with all the information at hand and find out the truth about what's been going on in our own universe. Although there is one explanation for the pulsating that's been front and center this entire time, we've been trying to ignore it. The pulsating might not just be about light, it's possible that the star might just be ready to go supernova and explode, taking everything around it with it. Betelgeuse is currently in the later stages of its life cycle, much like other massive stars. Throughout its existence, it has been engaged in a balance between gravity and nuclear fusion reactions occurring in its core. But the balance doesn't last forever.